Welcome back to the deep dive. So today we're jumping into something really critical in modern AI system design. Our mission is to basically dissect this hybrid automation architecture that claims to solve, well, maybe the biggest challenge out there for enterprise AI.
Oh, absolutely.
How do you run these massive complex workflows? We're talking processing hundreds of pages of research without the agents just, getting lost or completely bankrupting your token budget.
It really is the defining challenge right now. I mean, when you look at the source material, you see this constant tension.
Right.
On one hand, you have to have rigid control. Businesses need outputs they can trust, that are auditable, that follow a specific set of rules.
Predictable.
Exactly. But on the other hand, the whole reason we're excited about agents is their autonomy, that ability to problem solve, to handle things you didn't expect.
That balance, control versus autonomy, it feels like the white whale of automation. And the sources we're looking at, they seem to point to one major technical problem holding it all back.
The context bottleneck.
The context bottleneck.
Yep.
We've all seen how powerful LLMs are. They can reason, they can write, but their memory, the context window, it's tiny, it's temporary, and it is incredibly expensive.
So if you ask an agent to, say, summarize a 500-page report.
Right, and then you try to keep that whole 500-page text in its memory for every single step after that, analysis, drafting, everything, the system just falls apart.
Latency goes through the roof, costs explode.
An agent literally forgets what it was supposed to do in the first place.
Okay, so let's unpack the solution they're proposing. The blueprints lay out this 3-layer hybrid architecture. It's an integration of CrewAI Flows for orchestration, something called deep agents for cognition, and then Anthropic skills, and a model context protocol for tooling.
And the real genius of it seems, isn't some brand new tech. It's about discipline. It's about being incredibly strict about where data is allowed to live and how the agent gets to see its own capabilities.
A perfect summary. So it's an architecture built on isolation. That's it. You impose strict rules from the top. That's your control. And then you push all the heavy data and the actual work out into this external file-based memory. That's how you get scalable autonomy.
And by doing that, the context window stops being the bottleneck.
It frees up the LLM to do what it's actually good at, high-level reasoning and coordination.
All right, let's dive into that first layer, orchestration. This is where you have to make the big choice, right? Do we go with pure autonomy, just give an agent a huge goal and hope for the best? Or do we lock it down with pure structure, a traditional brittle script?
And we know from, well, a lot of painful experience that both of those extremes just don't work at scale.
So what's the problem with pure autonomy? Why not just let the agent run wild?
Because it gets lost in rabbit holes. I mean, think about a research agent. It finds one interesting little fact, starts digging into that, and 10 minutes later, it has completely forgotten its main goal. The outputs are inconsistent, unreliable.
And you have no idea what it's doing.
It's a black box. You often have to step in and manually pull it back on track.
Okay, and the other side, the pure script.
Too brittle, like you said. The real world is messy. An API you rely on returns a weird error, or an imp file has a slightly different format. A hard-coded script just breaks. It grinds to a halt.
So you need the reliability of a structure, but with the agent's ability to adapt.
And this is where the architecture brings in CrewAI Flows as the backbone of the whole operation.
Okay, so what are CrewAI Flows exactly?
The sources define them as the highest level of organization. It's the business process manager. It brings together the power of multi-agent crews with, and this is a quote, the precision and flexibility of procedural programming.
So it sets the high-level plan, but doesn't micromanage the agents.
Precisely. It dictates the sequence of events, but not the internal granular thinking of the agents doing the work.
And the real trick here, the innovation, it's not just about, listing tasks in order.
No, not at all. It's about moving completely away from that linear script model. It's all about an event-driven system.
Event-driven, so what does that actually mean in practice?
It means the flow is built out of components that react to things happening. The control comes from these decorators, like at start and at listen.
At start sounds pretty self-explanatory.
It is. It kicks the whole thing off. Maybe a user uploads a new file or gives a complex goal. That's the trigger.
And at listen is the clever part, I'm guessing.
That's where the adaptability comes from. The at-listen decorator makes sure that the next step only triggers when a previous step has formally and successfully completed.
So it's not do B after A, it's Listen for A to be finished, and once it's confirmed done, then trigger B.
Exactly. So if the getUser-input method finishes and updates the state with validated data, the flow hears that event, and then it kicks off, say, a create a guide outline. It creates this clear, observable structure.
And if a step fails?
The flow just stops. It gives you an immediate place to look for the problem. That's how you get control in a system that's still dynamic.
That makes a lot of sense for control. But what about cost? The sources really stress this idea of hybrid execution. Why is it so important for the flow to mix and match how it does things?
Efficiency. Pure and simple. Not every task needs a whole team of agents collaborating. That's expensive. It's a lot of LLM calls, a lot of back and forth.
Sometimes you just need a simple, structured output.
Right. And for that, the flow should use the cheapest, fastest tool for the job.
So can you walk us through an example? How does that play out?
Sure, let's take their guide creator flow example. The very first step is just to create an outline. It needs to be structured, but it doesn't require deep creative thought.
Okay.
For that, the flow makes a direct, cheaper LLM call. It uses a utility like LLM response format guide outline. That response format part is key. It forces the LLM to spit out a perfect JSON that matches a pydantic model. It's fast, it's cheap, it's reliable.
But then later when you actually need to write the content.
Exactly. When the flow gets to a step like draft content section, it completely changes gears. It spins up a full multi-agent crew. You get a content writer agent working on tone and substance, and maybe an educational reviewer agent critiquing it for clarity.
Which is much more expensive.
Much more. But it's necessary for that high-quality, nuanced result. The flow is like the switchboard operator, making sure the right amount of brain power is used for each specific task.
It's a utility maximizer.
Yeah.
Okay, let's talk about the guardrails themselves. You mentioned pydantic models. Now, most of us know pydantic for, data validation. How does it work as a guardrail for an agent?
This is a super important detail the sources hammer on. The pydantic models like guide creator state or section draft, they do way more than just check data types. They are the contract between the different parts of the system.
A contract.
Yes. If an agent's job is to create a section draft, the pydantic model is the spec sheet. It must have a title that's a string, keywords that are a list of strings, and body content that's a string under 5,000 characters.
And what if the agent messes up? If it breaks the contract?
That's the guardrail in action. If the agent tries to return just a blob of text, or it forgets the keywords list, pydantic validation fails instantly. The flow doesn't just move on with bad data, it throws an error.
It's a hard stop.
A hard stop. It says, this agent did not do its job according to the schema. This forces data integrity through the whole pipeline. The main state object tracks these milestones, like outline created, and because it's validated, you know for a fact that the data behind that milestone is perfect.
That's a pretty strict constraint. You literally cannot pass bad data down the line. So the orchestration layer gives us the structure and control, but we still have this huge problem of the data itself, the massive token guzzling data, which brings us to round 2.
Right. And this next part, this data strategy, it is absolutely non-negotiable if you want to operate at enterprise scale.
The sources call it the zero content state rule.
The zero content state. I like that. So the big debate here is, how do we process, let's say, a 500-page financial report without the token meter just spinning out of control?
Before we get to the solution, we have to understand the trap. The sources call it the intermediate result trap. This is, I think, the #1 reason agent projects fail on cost. Okay, let's break that down. Let's say I have an agent, and its job is to go through 100 pages of meeting notes and pull out all the action items for the marketing team.
Perfect example. The old, broken way to do it is this. The agent uses a tool to read the 100-page document. Then, to figure out what to do with it, it pastes the entire raw text, all 80,000 tokens of it, into the LLM prompt.
Whoa.
The LLM burns 80,000 tokens just to see the data. Then, if the agent needs to do another step, like summarize those action items, it has to put all 80,000 tokens back into the next prompt.
So the same raw text gets processed over and over again, once by the tool and then multiple times by the LLM.
You've doubled your cost right there. Latency is terrible, and you're almost certainly going to hit the hard context limit of the model, which causes it to fail anyway.
And that's why this zero content state rule is so important. It's built on what they call the map versus territory rule.
Yes, this is a critical decoupling. You have to create a strict separation between where the process lives and where the data lives.
Okay, what's the map and what's the territory?
The map is the process. It's held exclusively by the orchestration layer, the CrewAI flow. And that state, the map, must be super lightweight. It should never, ever contain raw content.
So if the flow needs to know about that 500-page report,
The state object only holds a reference, a file path, just the string, .workspace-financial-report.pdf. That's the map.
got it. And the territory?
The territory is the actual data, the 500 pages.
Yeah.
And it lives on the file system, in a workspace. Only the agents are allowed to go into the territory and manipulate it. They get the file path from the flow, they do their work.
They read from one file right to another.
Exactly. They read input.md, process it, and write the summary to summaryq3.json.
And when the agent is done, it doesn't report back to the flow with the 5,000-word summary.
No, it reports back with another tiny string of characters that says, your summary is ready at workspace summaryq3.json.
And this is the part I love, the hard constraint they mentioned in the sources.
Oh yeah, this is the kicker.
What is it?
The global flow state object. It's not allowed to exceed 5 kilobytes.
Wow. 5 KB, that's nothing. That's brutally small.
Exactly. It forces you to be disciplined. You can't cheat. If the state tried to hold that 5,000-word summary, it would instantly fail. It has to hold the file path, which is maybe 50 bytes.
By making that a non-negotiable rule, you guarantee the orchestrator stays nimble. It's just coordinating references, not acting as a giant, expensive data buffer.
It completely changes how you think about agent communication.
Yeah.
You start passing around these huge blobs of data, and you start passing around tiny, efficient pointers, like sending a URL instead of emailing a 500-page attachment.
This feels like the bedrock of scalability. If I need to process 10,000 documents, the cost of my orchestrator doesn't explode with the data volume.
And that's the key takeaway here for you. The instruction set, the plan, the pedantic models that stay small and cheap even if the data territory grows to be enormous. Without this pass-by-reference discipline, you just can't scale. It's technically and economically impossible.
Okay, so we've got the structure from the flow and the data discipline from pass-by-reference. Now let's get into the engine room, the agent itself, what the sources call the deep agent. The big question here is about agent drift. How does an agent remember a complex goal over dozens of steps if its context window is so limited? How does it maintain long-term memory?
Agent drift is the curse of any long-running agent process. As the conversation gets longer, those critical instructions from the beginning, the constraints, the target audience, they get pushed out of the context window.
And the LLM only knows what it can see right now.
Exactly. So it starts to drift, it forgets things. The deep agent architecture gets around this by using the most reliable external storage there is, the file system. It gives the agent an external brain.
An external brain. I like that metaphor. So how does the file system actually work as a memory?
Well, instead of trying to cram 10,000 words of notes and context into the prompt, the deep agent uses simple tools like read file, write file, edit file. When it gets a task, it immediately writes the important stuff, the goal, the constraints, an intermediate result to a file on disk.
So it's like the agent is taking notes in a notebook.
A digital notebook.
Yeah.
So if it needs to refer back to the summary of section 1 while it's writing section 3, it doesn't need to hold section 1 in its active memory. It just reads its own notes from the file system.
Which saves a massive amount of tokens and makes the whole process more reliable.
It's a fundamental shift. The LLM's context is for reasoning, not for storage.
Okay, that makes sense. And that connects to the second capability here, planning and decomposition. The agent can't just have a single high-level goal from the flow if it's a huge task, right?
Right. The flow tells the agent what to do and when. The deep agent is responsible for the internal how, and it's equipped with this really critical tool, often called write-to-dos.
Right to do.
Yep. So the flow gives it the big goal, like create a 10-section guide on hybrid cloud infrastructure using the research in this PDF.
That's a huge undertaking.
It is. So the agent doesn't try to do it all at once.
Okay.
The first thing it does is use write-throughs to break that massive goal into small, concrete, trackable steps.
Like what?
Like, step 1, analyze competitive guides and write my findings to a temp file. Step 2, draft the main pedantic outline for the guide and save it. Step 3, spin up a crew to draft section 1. It creates its own internal project plan.
And that to-do list is also saved to the file system.
Yes, so it can manage its own progress, check things off, and even change its plan if it learns something new along the way.
I can see how that's critical for long-running processes. But what about tasks that require context isolation? Let's say I need to analyze 5 different companies. I can't let what I learned about company A bleed into my analysis of company B.
Perfect use case for the next feature, sub-agent delegation. The main deep agent, the coordinator, sees this task and recognizes it needs 5 separate, clean streams of research.
So it doesn't do the work itself.
No, it acts as the manager. It spawns 5 specialized temporary subagents, and it delegates one specific isolated task to each one. You go analyze the 10K for competitor A.
And that subagent is in its own little context bubble.
Exactly. Its context window only contains data and instructions for competitor A. Meanwhile, the main coordinating agent's context stays clean, focused only on the high-level plan and putting the final pieces together.
So the subagents do the deep dives, write their findings to files.
And then report back to the main agent. This prevents what you could call cognitive pollution, where the main agent gets confused trying to hold 5 different complex topics in its head at once.
So the deep agent is smart enough to know when to delegate, and it uses the file system as a persistent memory to achieve the context window limit.
It transforms the LLM's transient memory into reliable long-term storage. And the result is an agent that can handle real complexity without crashing or forgetting its mission.
All right, we've built the structure with flows in the brain with these agents. But there's one last major source of inefficiency: how the agent actually uses its tools. This brings us to the classic dilemma: the Swiss Army knife versus the tool shed.
Right. Do you give the agent every single tool it could possibly need right from the start?
Or do you make it go find the right tool for the job only when it needs it?
And the Swiss Army knife approach is a huge reason why so many agent systems are slow and expensive. When you load the definitions for hundreds of different tools, a Google Sheets tool, a Jira tool, whatever, you are stuffing all of that descriptive text into the agent's context window.
And those definitions cost tokens.
Real tokens. If you have thousands of enterprise tools, that initial context load could cost you thousands of tokens on every single turn, even if the agent just wants to do a simple calculation.
And it's not just the cost, is it?
No, it's worse. It hurts reliability.
Yeah.
You overwhelm the model with options, and it increases the chance of tool hallucination, where it picks the wrong tool or makes one up because the prompt is just too noisy.
Okay, so the architecture solves this with a couple of innovations, starting with progressive discovery.
Right. Implemented with systems like Anthropic skills, progressive discovery basically turns that Swiss Army knife into a tool shed. The agent doesn't carry every tool, but it has a map of the shed and knows what's inside.
How does that work in practice?
It's a really clever 3-level disclosure system built around this SKILL.md file that lives with each tool.
Okay, let's walk through those 3 levels, because the token savings here sound massive.
They are. So level 1 is metadata. When the agent starts up, it does not load any tool code. It only loads the YAML front matter from the skill.md file. That's usually just the tool's name and a 1-sentence description.
So it's just seeing the signs on the doors in the tool shed.
That's the perfect analogy. And for a huge library of tools, this might only cost about 100 tokens in total. The agent just knows, okay, a tool for financial analysis exists over there.
And then, only if it decides that tool is relevant, it moves to level 2.
Level 2 is discovery. Now, the agent uses a tool to read the full body of that skill.md file. This has all the details, the instructions, the functions, signatures, everything it needs to actually use the tool. This might be a few thousand tokens.
But, and this is the key, it's loaded on demand.
Only when that specific complex tool is actually needed. It keeps the agent's active memory light and cheap.
And level 3 is just execution.
Execution. The agent has the instructions, it makes the function call, and the tool runs, probably using the file system workspace we already talked about.
So you pay 100 tokens to see the menu and only pay the full price for the one dish you actually order.
Exactly. It lets you have a massive library of capabilities without the massive upfront cost.
That solves the tool discovery problem. But what about the data itself? What if the task involves a huge data set, like filtering a massive spreadsheet? Direct tool calls are still a problem there.
That's the other half of the solution. The Model Context Protocol, or MCP.
Yeah.
MCP is a secure server-side environment where the LLM can have code executed for it. It's designed specifically to avoid processing raw data inside the LLM's context.
Because the old way would be to pull all 10,000 spreadsheet rows into the prompt to filter them.
Which would be over 100,000 tokens just for a simple filter. It's insane.
So with MCP, the agent goes into what they call code mode. It writes a script instead.
Exactly. The LLM's role shifts. It's not a data processor anymore. It's a code orchestrator. It sees the task, recognizes it's a data job, and writes a Python or JavaScript script to do the work.
And it sends that script to the MCP server.
Right. The server executes the script in a secure, sandboxed environment, The script does all the heavy lifting, the filtering, the aggregating, and, critically, it sends only the final answer back to the model's context.
Let's put some numbers on that. The sources say 10,000 row analysis.
Doc consumes less than 1,000 tokens. That's for the generated code and the final result combined. Compare that to the 100,000 plus tokens for the old method.
The difference is staggering. It's like asking a CEO to manually sort mail versus asking them to write a one-line command to have it sorted automatically.
The former is a waste, the latter is scalable.
And there's a huge privacy benefit here too, right?
A critical one. Since the data processing is happening remotely on the MCP server, you can build in automatic redaction or tokenization of sensitive information, like PII.
So the sensitive data never even enters the LLM's context window.
The LLM only ever sees the anonymized, aggregated results. This is how you automate workflows in regulated industries while staying compliant.
It's amazing. Every single piece of this architecture, from the flows to the tooling, is designed to minimize tokens while maximizing control and cognitive power.
So we've gone through 4 really technical rounds here, looking at structure, data, cognition, and tools. To tie it all together, the sources use this one really elegant analogy that I think makes it all click.
The public library.
The public library. It's the perfect model for how these layers achieve this balance of controlled, scalable autonomy.
Okay, so let's start with scalability and control. The CrewAI flow is running the whole show. In the library, that's the librarian.
Exactly. The librarian is the master coordinator. But the librarian does not try to memorize the content of every book in the library.
That would be the context bottleneck.
That's the failure mode. Instead, the librarian manages the card catalog. And the card catalog only contains references, call numbers, file paths. It never contains the raw text of the books.
Which keeps the whole system lightweight and scalable, whether there are 10 books or 10 million.
Precisely.
Okay, next up, focus. The deep agent. This is the one doing the actual thinking without getting overwhelmed. So in our analogy, this is the researcher.
The researcher gets a call number, a reference path from the librarian, and goes into the stacks. The stacks are the file system, the workspace.
And they do their work in the stacks.
Right. They read the books there. They take notes in their own notebook. That's write to-dos and write file. And when they're done, they just bring the final summary or the location of their saved notes back to the librarian.
They don't lug the entire library's contents back to the front desk every time.
Never. That's the context isolation we talked about, achieved with that external memory.
And finally, efficiency. The tooling layer, progressive discovery, and MCP.
That's the equipment room in the library. Think microfilm readers or high-speed scanners. The researcher doesn't carry all that heavy equipment around all the time.
Right, that would be crazy.
They just see a sign on the door, that's the SKILL.md metadata, that tells them what's available, that's progressive discovery. They only go in, read the manual, and use the specialized gear if the task actually requires it.
And that specialized gear, that could be the MCP server for heavy data processing.
Exactly. If they're just writing a quick summary, they walk right past the room, saving all that energy, all those tokens.
It all comes back to that zero content rule at every layer. The LLM reasons, the file system stores, and the MCP processes.
That abstraction, that strict separation of concerns is the real breakthrough. It solves for control, autonomy, and the context limit all at the same time. It's a blueprint for a system that's robust, scalable, and actually affordable to run. So the final verdict is pretty clear. This hybrid architecture really does offer a viable path for scaling complex agentic systems inside an enterprise. It gives you structure and consistency with CrewAI Flows. It gives you deep autonomy with deep agents and their external brain. And it gives you incredible efficiency through pass-by reference and this on-demand tooling. We are finally moving past the limitations of the context window.
And you now have the blueprints for how to build these kinds of workflows that go far beyond what a single context-bound agent could ever do. This really puts you at the cutting edge of automation design. But, solving one bottleneck always reveals the next one. Which brings us to our final provocative thought for you to consider.
Right. If the LLM is no longer a data processor, if it's not manually sorting things anymore, and it's becoming this highly effective code orchestrator.
Your master planner, writing the scripts.
Then we've just swapped one problem for another. The LLM is now generating code Python or JavaScript that runs critical business logic on huge data sets inside that MCP environment.
So the new bottleneck isn't context size, it's the quality of the LLM's code. It's reasoning and its ability to write correct, robust, secure code.
Exactly. When your whole workflow depends on AI-generated code, how do you trust it? How do you validate it? How do you put formal guardrails around the code itself?
That level of code fidelity, that feels like the next frontier we're all going to have to master.
That's the question that will define the next generation of these platforms.
Something to think about until our next deep dive. Thanks for joining us, and we definitely encourage you to look deeper into pydantic state management and the mechanics of progressive discovery.